Classifying numbers. Well, by now in your math experience, you've probably seen many, if not all of these numbers before. We have numbers like pi that have unending digits. We have improper fractions like 10/7 or fractions like 3/4. We have prime numbers that probably you've studied about, 2, 3, 5, 7, and so on. We have repeating decimals like 0.3333333, that little line over there. And we've got even numbers, numbers under a radical, perfect numbers like 6. We have the number e. We have a number that's not really a number at all, infinity. Decimal numbers, 1.25, and a number that actually represents no quantity. One of my favorite numbers, 0. So mathematicians had to find a way to kind of classify these. People really like to classify things, and so mathematicians have a whole system that they have invented to classify our numbers, to tell us a little bit about them. The first one is the natural numbers. It's probably the first set of numbers you actually learn how to use. When you're first learning to count, you use the natural numbers, and that just includes 1, 2, 3, and so on and so on. No negative numbers in there. Sometimes mathematicians put a 0 in there, and then they get rid of that next category, but I like to keep 0 in a whole category of its own. So in the whole category, the next set of numbers are the whole numbers. Now the whole numbers include all of the natural numbers as well as 0. So 0, 1, 2, 3, as far as you can count. Integers include negative numbers and also 0. So integers include all of those numbers as well. So let's put a circle around there. So integers include all of the whole numbers, so it's got 0 in there, the natural numbers, which are in the whole numbers, and all of the negatives of those numbers. Now, rational numbers are kind of fun because you can represent them as a fraction. That a and the b are just integers. B cannot be 0. We cannot divide by 0. But anything that can be written as a fraction is a rational number. Now, it looks like that's probably the end of our numbers, but we know that there are numbers like pi that can't be written as a fraction. In fact, for a long time, this was thought to be all of the numbers there were. Pythagoras, a long time ago, was studying triangles and came across some numbers that didn't quite look right to him. But he ignored that because he was very set on believing that everything was a rational number. Rational numbers include all of these. Rational numbers include integers and natural numbers because 2 can be written as 2 over 1. So Pythagoras had some students that kind of started exploring these sides of a triangle, which didn't seem to be able to be written as a fraction. He got very upset by this, so upset, in fact, one of the students who was exploring this had an untimely death of drowning. But as mathematicians continued on, they found that, yes, indeed, there are irrational numbers. Numbers like pi and numbers like the square root of 7. These numbers have digits that continue on but have no specific pattern. So you can't find a pattern in there, so you can't write it as a repeating decimal. Numbers like square root of 2 and numbers like e. So now our number base is broadened, and we actually have all of these encompassed by the real numbers. Now I know what you're thinking, all numbers seem real to you, but remember this when we go on, there are some numbers that actually don't fit into our real numbers, but for now, we're just going to be talking about the real numbers. Okay, so let's look at a way we can classify these numbers. I have a little check mark I need to fix over here. And let's look at the number 8.5. I'll write that a little better. So if we're looking at our numbers, we can almost think of like each of these as a room that they're going in. So our real numbers, we're only talking about real numbers right now, so I'm leaving that door open so all of the numbers can go through the real number door. To be an irrational number, you have to not be able to write it as a fraction. And so that door's closed for now. And then we've got our rational, we've got our integers, we've got our whole and our natural numbers. So let's look at the number negative 8.5. Now, negative 8.5 is a real number, so it's going to be able to go through that door. We can write negative 8.5 as a fraction of integers. We can act that's the same as 8.5, negative 8.5, or negative 17/2. So we can write it as a over b. B is not 0, so we're going to let it go through that door. But it's got a fractional part, so it cannot be an integer. Anything that's an integer cannot have a fractional part. So 8.5 is a real number, which my black represents that, and is also a rational number with the green check mark. Let's look at the next one. Let's look at square root of 5. Now, square root of 5 is a decimal number, but the decimal goes on forever. There's no repeats in there. Your calculator will actually round it if you push square root of 5 on there. But we know it's a real number because we're only talking about real numbers, and we cannot write it as a fraction. So it must go through the irrational door right here. So that number, square root of 5, is a real number and an irrational number, and my brown represents the irrational. Now let's look at a number like 2. So 2 we know is a real number. We can write 2 as a fraction, so it's a rational number, 2 over 1. 2 is an integer. It has no fractional parts. And 2 is a whole number. It's included in here. In fact, 2 is a natural number. It's actually one of my examples right there. So 2 meets all of these. It can go in all of these rooms. So we have real, we have rational, we have integers, we have whole, and we have natural numbers. 2 is all of those. Now let's look at the next one. Square root of 4. Square root of 4 might trick you a little bit because we see some square root signs in there. But you have to look at the number simplified. Square root of 4 we know is 2. And so we can actually just use the simplified form of this to figure out the categories this fits into here. It's a real number we know. We can write it as a fraction, that's 2 over 1. It is an integer, it has no fractional parts. It is a whole number and a natural number and actually meets all of the same criteria as the 2 above. Now the last one, negative 14/2. Got a fraction right there, but that's not in its reduced form. Its reduced form is negative 7. Negative 14/2 is the same as negative 7. We know negative 14/2 is a real number. We know negative 14/2 is a rational number. It's actually written in that form. And we also know it's an integer because this is the same as negative 7. So it is allowed in that integer door, but not into the whole numbers door because the whole numbers include only positive numbers. So we have it's a real number, a rational number, and an integer. Okay, we're ready to look at some formal ways of expressing what categories these numbers are in. So let's first look at the natural ones. Our natural numbers are often represented by n. Mathematicians, I wouldn't say are lazy, just very efficient. And so sometimes if they want to talk about just the natural numbers, you can just put an n down there. Now remember, this means set of. It's like a little plastic shoebox that contains what we're talking about. It's the set of. And we have a 1, 2, 3, and dot, dot, dot. The dot, dot, dot just indicates that it continues forever. We go to 4, 5, 6. Natural numbers are non-negative counting numbers. Now remember I said sometimes mathematicians put a 0 in there and they take out this whole category, but I think it actually belongs in this whole category from my personal standpoint. Sort of a personal preference here, how you like to classify it. Whole numbers do not have an abbreviation, so maybe that's why they like to include 0 in there. But whole numbers include, they are the set of 0, 1, 2, 3, and there's that dot, dot, dot again. Non-negative counting numbers plus 0. Integers are represented by a z. Now that z is actually the beginning of the word, the German word, a Zahlen, for numbers. And so our set of integers include the negatives. So the dot, dot, dot comes before. That means all the way back on those negative numbers, all the way forward. And it has no fractional parts. So the counting numbers and their negatives, and of course 0. Rational numbers represented by Q. I have no idea why rational numbers are represented by Q. And this set notation is a little bit tricky, so let's look at the definition first and then I'll explain this. Rational numbers are a ratio of an integer and a non-zero integer. So the denominator can't be 0, and we know that because we can't divide by 0. Now let's take a look at the set notation. We've got our sets right here, our container, and we have m divided by n. Now the m and n are variables that we're going to use to express this. So m divided by n, this line means such that. So it's going to give us some criteria, some stuff about m and n. So m divided by n such that m and n, m comma n, are elements in Z. That's what this little funny E means. It's elements in Z. So that means it belongs to the Z set. And remember, Z are integers. So this really just says m and n are integers, and n cannot be 0. So those are our rational numbers, just basically telling us it's a fraction made out of integers with the denominator not being 0. Irrational numbers, a number that cannot be written as a fraction. That also means it can't be written as a repeating decimal, because remember, we can write all repeating decimals as fractions. And real numbers, any number on a number line. We can actually put pi on the number line. It is in there. It is between 3.1 and 3.2, and so we can put pi in that number line. So any number that can go on that number line. And we'll learn later numbers that can't go on that number line, and that will make Pythagoras, I would imagine, very upset.